Now in this lesson, we'll study about the potential. That is, the initial sections we'll study about potential, and the final sections we'll study about capacitance. Okay. Potential is always related to work done, potential energy or work done, isn't it? Now, generally, potential energy means the work done is converted into energy and is stored in a system. That is the potential energy. In the previous classes, you might have studied that potential energy is developed because of its position or orientation. Okay, kinetic energy is developed because of its motion, and potential energy is developed because of its position or orientation. And because of its position or orientation, certain strain or work is done on the system, and that work done is converted into energy and is stored in the system. Okay, that is the potential energy in general. Now, potential energy in the case of electrical charge is, if you want to take one charge from infinity and want to place at a particular point, we have to do some work done there. Isn't it? If it is empty space, if there is no any other charge there, we can simply bring a charge and keep it there. If there is no acceleration, there won't be any force required and there is no work done there, isn't there? So in an empty space, we can bring any charge and keep at any position without any work done. But suppose one positive charge is there at this position and we are bringing another positive charge near to that. So positive and positive will repel, isn't it? So we have to bring the charge against that repulsion and want to keep at a particular position. So for that we have to do some work done, isn't it? And that work done is converted into energy. That is the potential energy of a charge system. Okay. So potential energy of a charge system means for placing each charge in particular position in the space, we have to do some work done, and that work done is converted as energy and stored in that system, in that electrical charge system, and that energy is known as potential energy in the case of electricity or electrical field. So that's all about potential energy of a charge. Now potential means if we are bringing a unit charge, okay, not any amount of charge, we are bringing a unit positive charge and keeping at a particular position, and that work done is known as potential. Okay, the difference between potential energy and potential is that potential energy is to bring all the charges and keep at that particular position, that total work done. Okay, potential means we are bringing unit charge. Okay, a positive unit charge we are bringing from infinity. Unit charge means its value will be 1 coulomb. Okay, so we have to take one charge from infinity, not any charge, 1 coulomb charge plus 1 coulomb charge, that is positive test charge, that is known as test charge, because that is we are using to test the value of electric field or force or voltage, etc. Voltage in the sense potential, etc. So that is known as test charge. Test charge value will be plus 1 coulomb. Unit charge, positive charge. Okay, so plus 1 coulomb charge we are bringing from infinity and keeping at a particular position. And for that we have to do some work done, and that work done is converted as energy, or corresponding to that, that work done is known as potential. Okay, so potential, electric potential is the work done to bring a unit positive charge from infinity and to keep at a particular position. That is the potential at that particular point. Various units for potential. V or volt. That is one unit for potential. This is we are using commonly. Then another unit is, I told you, it is the work done per unit charge. It is the work done to bring a unit charge. So also we can write as W by Q. Potential, it can be written as W by Q. It is the work done to bring a unit positive charge. So V equal to W by Q. So another unit for potential is work done, that is joule, and charge is coulomb. So another unit is joule per coulomb. So volt V is there. Otherwise, joule per coulomb is there. Also, work done we can write as force into distance, isn't it? F into D, force into distance. So also another unit we can derive from here. Force is Newton and distance is meter divided by charge, that is coulomb. So Newton meter per coulomb. So these three units can be used for potential, and commonly we are using only V. But remember, these two are also the units for potential. We can define 1 volt from this equation. So from this, potential V is equal to work divided by charge, W by Q. So 1 volt we can say if work is 1 joule, if charge is 1 coulomb. Okay. So 1 volt is defined as the work done. If we have to do 1 joule of work done to bring 1 coulomb charge to a particular point, then the potential at that particular point is 1 volt. Okay. So if you want to do 1 joule of work done to bring 1 coulomb charge to a particular point, then the potential at that particular point is 1 volt. That is the way how to define 1 volt. Now, potential difference. Potential means, as I told you, if you want to keep one charge at a particular position, we have to bring a work done. So that work done is known as the potential at that particular point. Now, we have 2 points. This is A and this is B. Potential difference between these 2 points will be, if you want to bring one charge from, basically 1 coulomb charge from one point to the other point, that work done is known as potential difference between these 2 points. Okay, potential at a particular point means it is the work done to bring a charge from infinity to that point. Now, potential difference between 2 points means it is the work done to bring a charge from one point to the other point. The equation we can write as delta W by Q. Delta W indicates the work done to bring a charge from one point to the other point. Now, we are going to derive one expression for electrostatic potential due to a point charge at a particular position. Okay. We are going to derive the expression for potential due to a point charge. So, at this position, we are having a point charge, that is a charge of value capital Q. And we are going to derive an expression for potential at this point P. We are going to derive the expression for potential at this point P, and that point is at a distance of R from the charge. Okay. So we are going to derive the expression for potential at this point, which is R distance from a particular charge Q. Okay. And from the definition, we know that potential at a particular point is the work done to bring a unit positive charge from infinity to that particular point, isn't it? So, from infinity, we can bring through any path. The path structure is not important there. Now, we are assuming that it is a straight line. So, from infinity means large distance. From infinity, we are going to bring a unit positive charge, which is known as test charge, and going to keep at this particular position. Okay. Now, the expression for work done is equal to force into distance, isn't it? Now, we are assuming a small distance dx here. Okay. So, dx is a small distance in between that motion, which means from infinity to P, between that we are taking a small path difference, that is dx. Now, the expression for force is, suppose this is at a distance of x from the charge. This length element is at a distance of x from the charge. Now force is equal to, we know force is equal to 1 by 4 pi r square, isn't it? Here 1 by 4 pi epsilon 0 q1, that is capital which we are bringing, and the value of that charge is plus 1 coulomb, isn't it? So into 1, q2 will be 1 coulomb divided by r square. Now the distance is x, so it will be x square. So the expression for force is equal to 1 by 4 pi epsilon 0 q divided by x square, isn't it? So force we can substitute here. So work done is equal to F, that is 1 by 4 pi epsilon 0 q divided by x square. And we got the expression for, actually this is not the total work done, this is a small work done to bring the charge through this small length element dx. So we can write it as dw, small work done between that. Now potential is actually the total work done to bring the charge from infinity to this point. So V will be integral of dw, or summation of all such work done will give the potential or the total work done, isn't it? So potential is equal to integral of dw, or the summation of each work done, that is equal to integral of dw is this one, that is 1 by 4 pi epsilon 0 q divided by x square into dx is there. Okay, dw is equal to force into dx. This is the expression for force into dx. So dw is equal to integral of 1 by 4 pi epsilon 0 q by x square into dx. And we have to do the integration from infinity to r. In this position, we are going to find the potential. So integration from infinity to r. And also we are doing the work done against the field here. So there is a negative sign also. This negative sign indicates that we have to do the work done against the repulsive force between the charges. So a negative also there. Now just integration, all the constants we can take out. So V is equal to 1 by 4 pi epsilon 0. This Q is a constant. The amount of this charge is constant. So we can take out. Then minus sign is there. Infinity to R 1 by x square dx. Now only this integration. Generally, okay, now integration V equal to minus 1 by 4 pi epsilon 0 q integral infinity to r 1 by x square we can write x raised to minus 2 dx, isn't it? 1 by x square we can write x raised to minus 2 dx. Now general expression integral x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. Here it is x raised to minus 2. So integral x raised to minus 2 dx is equal to x raised to minus 2 plus 1 divided by minus 2 plus 1. That is equal to x raised to minus 2 plus 1 is minus 1 divided by minus 1. So this is the expression there that we can substitute there. It is equal to minus 1 by x. X raised to minus 1 we can write 1 by x. Negative is also there. So minus 1 by x. Then we can write the V equal to 1 by 4 pi epsilon 0 q, and integral of this one is minus 1 by x. Already there is one negative, isn't it? That negative and this negative will cancel. 1 by x, and limit is from infinity to r. And how we substitute the limit? Upper limit minus lower limit. So V equal to 1 by 4 pi epsilon 0 q into upper limit is r, 1 by r, minus lower limit is infinity, 1 by infinity. And 1 by infinity is 0. So for this, it will be 0. And you got the expression for potential now. That is V equal to 1 by 4 pi epsilon 0 Q divided by R. So this is the expression for potential due to a point charge at a particular position, at a distance R from the charge. Now, when we derive it, before this step, we got the expression like that, V equal to 1 by 4 pi epsilon 0 Q 1 by R, and there we bring the charge from infinity to a particular point because we were calculating the potential at that particular point. Now, if we need the potential difference, if this is A and if this is B, and if this is the charge Q, and A is at a distance of R1 and B is at a distance of R2 from the charge. Now, to bring the charge from B to A, we have to do some work done, that is known as the potential difference between these 2 points, isn't it? Now, here when we calculate the potential at a point infinity to that distance, so we substitute the limit infinity to R. Now, if we need the potential difference between these 2 points or between B and A here, now we are bringing the charge from R2 to R1. So the limit will be from R2 to R1. R2 to R1. So instead of infinity to R, when we calculate the potential difference between any 2 points, write it as VAB, is the potential difference between A and B. We have to give the limit as the distance between that distance to the 2 points from the charge. So here the limit will be R2 to R1. Okay. And if we simplify it, VAB is equal to 1 by 4 pi epsilon 0 Q into upper limit, that is 1 by R1 minus lower limit, that is 1 by R2. So this is the expression for potential difference between any 2 points. Potential difference is equal to 1 by 4 pi epsilon 0 Q into 1 by R1 minus 1 by R2, where R1 and R2 are the distance to the points A and B, and VAB is the potential difference between A and B. And from this expression we can understand that potential difference between the points are depends only on R1 and R2. That is, if this is the charge Q and if this is A and if this is B, this is R1 and this is R2, isn't it? Potential difference between A and B depends only on R1 and R2, which means if we bring the charge from B to A in a straight line or through a path like this or through a path like this, whatever it is, in the expression we have only R1 and R2. That means through any path we can bring the charge from one point to the other point, but potential difference depends only on the end points, not depends upon the path in which it brings. Okay, so which means electrostatic force is a conservative force. There only the work done is independent of the path but depends only on the end points. Here also potential difference depends only on the end points independent of the path. So electrostatic force is conservative force. Okay. Now another one thing. Electrostatic potential due to a system of charges. If we have Q1 charge here, Q2 charge here, and Q3 charge here, we need to calculate the potential at a point P at a distance R1 from Q1, R2 from Q2, and R3 from Q3. Okay. Now we know the expression for potential, that is 1 by 4 pi epsilon 0 Q divided by R. So, electrostatic potential at a particular point because of a system of charge will be the sum of each one. This is known as superposition principle. Superposition principle you already studied in the case of electric field and force, isn't it? Force is the force at a particular point will be the sum of forces because of each one, and total electric field at a particular point will be the sum of electric field because of each one. But force and electric field are vector quantity, so vector addition we have to do. Total force will be the sum of vector sum of individual forces. Electric field also same. But potential is a scalar quantity. There is no direction for it. It's only having value, magnitude. So V equal to V1 plus V2 plus V3 plus etc. Just algebraic sum of each one will give total potential at a particular point. That is the importance of potential. The calculation is easy than force and electric field here, because force and electric field were a vector quantity. We have to consider vector addition there, that is more complicated. But V is a scalar quantity, so scalar addition, that is simply algebraic addition, is enough. This is convenient to use here. So here total potential at P is equal to V1 plus V2 plus V3. Three charges are there. So 1 by 4 pi epsilon 0 Q1 divided by R1 plus 1 by 4 pi epsilon 0 Q2 divided by R2 plus 1 by 4 pi epsilon 0 Q3 divided by R3. 1 by 4 pi epsilon 0 is common, which we can take out, into Q1 by R1 plus Q2 by R2 plus Q3 by R3. If more than 3 charges are there, plus etc. So V equal to 1 by 4 pi epsilon 0 summation of Q by R. This is the potential at a particular point due to a system of charges if more than one point charges are present.